RB and line PB, and what we want to prove is line PB is the perpendicular bisector of ER. Now, for perpendicular bisector, first off, we know it's going to be perpendicular, meaning that the angles are going to intersect at 90 degrees. So we need to prove that both these angles are 90 degrees. Further, it's a bisector. So that means that ER is going to be cut in half, meaning that ES needs to be congruent to RS. If we can do both of those things, then we have proven that PB is the perpendicular bisector of ER. So, of course, we're going to go ahead and start off with our given information. PE is congruent to PR, and EB is congruent to RB. Now, at this point, all of these proofs are going to be detour proofs. So we're going to need to prove that two triangles are congruent, and we're going to have to do that twice with two sets of triangles. From there, we will be able to prove that it's a perpendicular bisector. So, looking at the two big triangles, triangle BEP and triangle BRP, is there anything that they have in common? Well, yes, they share BP. So I can say that BP is congruent to itself by the reflexive property. Because anytime that something is congruent to itself, it's always going to be by the reflexive property. Now, at this point, we do have enough information to prove that triangle BEP is congruent to triangle BRP. And if we look at these, the congruency marks, that is, we have side, side, side. So those two triangles are congruent by side, side, side. Now, at this point, we're either going to focus in on the triangles on the left, or we can focus in on the triangles on the right. But regardless of which triangles we decide to use, I'm going to use the ones on the right side, we're going to look for something that the big triangles that we just proved are congruent share, and something that the smaller triangles also share. So we're looking for something that they both share that they could have congruent. Now, we already have line segment PR and line segment PE. We already know that those are congruent from statement number 1. So I don't want to use those because it's already in our proof. So instead, let's focus in on some angles. Let's focus in on angle EPS and angle RPS. We can say that those two angles are congruent because, again, they're on the larger triangles and they're corresponding parts of those larger triangles. So if I were to do a rigid motion, if I were to reflect this triangle on bottom over line BP, these two angles, the angles that we just found, EPS and RPS, would fall perfectly on top of one another, meaning that they're corresponding angles. And if the triangles are congruent, which we see in statement number 4, then we know corresponding parts, which those angles are, corresponding parts of those congruent triangles are congruent. Now, at this point, we have a side and an angle. I need one more thing in order to prove that the two triangles on the right side are congruent, and that would be line segment PS. Now, you may be already saying, well, we already have the line segment, and it's in green here, but that's line segment BP, and that worked for the large triangle. But BP is not a segment for our smaller triangle, triangle ESP. However, SP is. So I can say that PS is congruent to PS. Anytime that something's congruent to itself, it's always by the reflexive property. At this point, we have enough information to prove that the two triangles are congruent, so I can say that triangle EPS is congruent to triangle RPS by side, angle, side. So those two triangles are congruent by side, angle, side. Now, the reason that we wanted to do that is because now we have ES, segment ES and segment RS, and those are corresponding parts. Further, they're corresponding parts of our now congruent triangles from statement number 7. So I can now say that segment ES is congruent to segment RS by CPCTC. And the reason why that's important is because that's telling us that BP is bisecting segment ER. And the reason for that is because, again, ER is being cut in half, it's congruent on both sides. From here, we're going to focus in on the angles, because again, we need perpendicular angles. So I'm going to go ahead and say that angle ESP is congruent to angle RSP. And again, those are also congruent parts within congruent triangles. So I can say that those two angles, before I do that, let's go ahead and say that PB bisects ER. And again, the reason why that's happening is because ER is being cut in half. So if a line divides a segment in two, then the segment is being bisected. So we can see that that is occurring. ER is being cut into two equal parts. From here, again, I'm going to focus on the two angles, ESP and RSP. So angle ESP is congruent to angle RSP. And the reason that we can say that these two angles are congruent is because, again, they're corresponding angles. They're corresponding parts of congruent triangles. And we know corresponding parts of congruent triangles are congruent. So the reason for that is CPCTC. Now, on top of that, I'm going to go ahead and say that those two are right angles specifically. The reason that we can say that these are right angles is because they're not only congruent angles, but they're also supplementary. And if we recall from our previous video about right angle theorems, our right angle theorem was if two angles are both congruent and supplementary, then they are right angles. So that's why we can say that these two are right angles right now. Now, if they're right angles, that means that they're perpendicular to each other. So from here I can say that PB is perpendicular to ER. And again, that's due to the right angles. So if two segments or two lines intersect at right angles, then they are perpendicular. Then lastly, we can finally say that PB is the perpendicular bisector of ER, which was our goal. And the reason that we can say that deals with statement number 9. We see that's bisecting. And statement number 12, where we see it's perpendicular. So we see that's a perpendicular bisector. So a perpendicular bisector intersects at a right angle, which we see, and divides the segment into two equal parts, which we also see. So at this point, this proof is now finished. We have proven that PB is the perpendicular bisector of ER. All right, so today we're focusing on 4.5, the equidistant theorems. This deals with equidistant all the way through. And what we started with, those perpendicular bisectors, that's the applications that we can use equidistant theorems with. So these equidistant theorems will all be dealing with perpendicular bisectors. Our learning target, well, the depth of knowledge is level 4, meaning that's fairly difficult. Lots of proofs today. And our learning target is I can write 2-column proofs involving triangles, isosceles, triangles, circles, and specifically what we're working on, the equidistant theorems. So we're going to be proving proofs using the equidistant theorems. So let's go ahead and jump right in. So first off, some basic definitions that we've talked about in the past, but good to know still. The distance between two objects is the length of the shortest path joining them. So if we have 2 points, the shortest path between those 2 points is a straight line, which is all this postulate's saying. The shortest distance between 2 points is a straight line. Now, distance. Oftentimes in your homeworks on your tests, they'll ask you for distance in these terms. So find the distance of RS, or what is the length of RS? So they'll be asking us to find distance quite a lot. Now, another way that you may see distance on tests, on standardized tests, meaning ACTs, SATs, all that stuff, you may see it with absolute value signs. So if you see a segment within absolute value signs, all this is asking for is distance. So keep that in mind as well. I won't be using that this too much, but I want to make sure that you guys can recognize it in case it pops up. I may try and throw a couple problems in there at some point just so that you guys can see it and so that you guys get used to it, but just know that this doesn't always occur. However, it is good to keep an eye out for it. Now, again, today we're talking about equidistant. Equidistant just means equal distance. It's in the name. So equa meaning equal, distant meaning distance. So when we see equidistant, we know it means equal distance. So x is equidistant from P and Q. So that means x is an equal distance away from both point P and point Q. And we can tell equidistant a lot just by using congruency signs. Congruency means the same. If two things are the same, they have the same measurement. And if they have the same measurement and we're dealing with sides, that means they have the same length. If they have the same length, that means that they have equal distances. So keep an eye out for that. Congruency signs just mean that they are equidistant from that same point. All right, so with that information, we should now be able to work towards our perpendicular bisectors. So getting started on that, first off, the definition of a perpendicular bisector is the perpendicular bisector of a segment is the line that bisects and is perpendicular to that segment. Meaning, in this case, AB is going to be the perpendicular bisector in both. So it will not only bisect, it will not only cut CD in two, but it will also intersect at 90 degrees, which we can see right here. It's bisecting, it's cutting it into two equal parts, and then it's perpendicular, meaning that it's intersecting at right angles. So that is the definition of a perpendicular bisector. Now, some theorems that we can use with perpendicular bisectors. First off, if 2 points are equidistant from the endpoints of a segment, then the 2 points determine the perpendicular bisector of that segment. So, the 2 points being points A and point B. So those are the 2 points that we're dealing with in each of these diagrams. These are equidistant from the endpoints of a segment. So we have segment CD here, and we can see that it's equidistant from CD. And we can see that with the congruency marks here. So if that's the case, it's equidistant from the endpoints of the segment. I'll just go ahead and draw those in. Then the 2 points determine the perpendicular bisector of that segment. The 2 points being points A and B, those points determine the perpendicular bisector, meaning that AB would be our perpendicular bisector. And this is oftentimes how you'll see it. So at this point, we would be able to say, okay, they're equidistant from the endpoints of the segment being CD. Then the 2 points, A and B, determine the perpendicular bisector of the segments, meaning points A and B is the perpendicular bisector of segment CD. So that's our first theorem. And again, it deals with equidistance, so look for that equal distances. And if you see equidistant like this, that automatically means that that segment is going to be the perpendicular bisector. Also, keep this in mind when we're dealing with kites in the next chapter. Kites will have this often, quite often, because one of their properties is that the diagonals, CD and AB, are perpendicular to each other. So just knowing this information helps us out a lot when we deal with kites and all these different quadrilaterals in the next chapter. All right, next up. The next theorem that we have also deals with equidistant and further deals with perpendicular bisectors. So it says if a point on the perpendicular bisector of a segment, if a point lies on the perpendicular bisector of a segment, in this case, AB is still a perpendicular bisector, and CD is being bisected. So that's the one that's being cut in half. If that's the case, if I have a point that's on the perpendicular bisector, then it is equidistant from the endpoints of that segment, meaning it will be the same distance to both endpoints that are being bisected. So if I draw another point on this other triangle over here, so I just draw any point, that point is lying on the perpendicular bisector. So what that tells us is that it will be the same distance from C as it is to D. So that's all this theorem states. Now this will help us out a lot because we'll be able to create more triangles, prove more triangles are congruent, and further along these proofs down the road with this theorem. But this will play a pretty good role down the road. If you see a point that lies on a perpendicular bisector, obviously you'd be able to say, oh, it's equidistant from both endpoints. All right, so next up, let's jump back into our proofs. So here is our next proof. Given angle 1 is congruent to angle 2, angle 3 is congruent to angle 4, we would like to prove that AE is the perpendicular bisector of BD. So to get started, we write out our givens. Angle 1 is congruent to angle 2, angle 3 is congruent to angle 4. Now, with this, we have two triangles, one up top, one down below. And with these two angles, these are base angles. So that means that this is an isosceles triangle. Triangle ABD is isosceles. So therefore, I should be able to say that AB is congruent to AD because if base angles are congruent, then legs are congruent. That's definition of perpendicular bisectors. That's some of our theorems not perpendicular bisectors. That's some of our definitions and theorems for isosceles triangles. Now, with that, I could say the same exact thing for the bottom part down here. So I can say that BC is congruent to DC for the same exact reason. If base angles are congruent, then legs are congruent. Now, there are multiple ways that you can go through this proof at this point. You can either use the reflexive property, but I'm going to do something a little bit different. I see angle 1 and angle 3. They are congruent to angle 2 and angle 4, respectively. So if I add angle 1 and angle 3, it should be the same as if I add angle 2 and angle 4. So therefore, I can say angle ABC is congruent to angle ADC by addition. The sum of congruent angles are congruent. So you can either say addition property, because we added them together, or you can say the sum of congruent angles are congruent. That's perfectly fine as well. Now, from here, we do have enough information to prove that the two triangles are congruent. If we look at it, we have side, angle, side. So I can say that triangle ABC is congruent to triangle ADC by side, angle, side. At this point, I'm going to go ahead and focus in on the top triangles once again. So I'm focusing now on triangle ABE and triangle ADE. Looking at these two triangles, I see that they share with the big triangle, they share side length AB, which we already have from statement number 3. They also share angle BAE. So I'm going to have angle BAE is congruent to angle DAE because these are corresponding angles. And further, they're corresponding angles within congruent triangles. So the reason I can say this is because if I see triangles are congruent, then I know corresponding parts of congruent triangles are also congruent. From here, I now have enough information to say that the top triangles are congruent. I have angle, the blue angle right here, angle 1. So angle, side, angle. So triangle BAE is congruent to triangle DAE by angle, side, angle. Now that those two triangles are congruent, I can focus in on the bisection portion of our proof. So again, we want to focus on bisection. So I can now say that BE is congruent to ED. And the reason I can say that is because if triangles are congruent, then corresponding parts of congruent triangles are congruent. Again, I'm going to do that with our angles as well. So angle BEA is congruent to angle DEA because CPCTC. Then lastly, well, not lastly, but close to lastly, if these two angles are congruent and supplementary, I can say that they are right angles. So angle BEA and angle AED are right angles. Again, the reason for that, if two angles are supplementary and congruent, then that means that they are right angles. If that's the case, we see perpendicular from the right angles. We see a bisection from statement number 9. We can now say that AE is the perpendicular bisector of BD because AE bisects BD and is perpendicular to BD. And with that, this proof is complete. All right, next up. Given PE is congruent to PR, EB is congruent to RB, we would like to prove that PB, line PB, is the perpendicular bisector of ER. So again, we start off with our given information, and then we're trying to prove the big triangles are congruent. So I see that they both share PB, so I'm going to go ahead and say that PB is congruent to itself by the reflexive property. At this point, I should be able to say that the two triangles are congruent. So triangle PEB is congruent to triangle PRB by side, side, side. At this point, I'm going to use the two top triangles as well as our big triangles. What do they share that is not already shown to be congruent? Well, the big triangles that we just proved are congruent and the triangles on top both share this angle, angle EPS. So I can say that angle EPS is congruent to angle RPS because these are corresponding parts and they're within our big congruent triangles. So the reason that we can say that is because we have congruency for triangles. So we can say corresponding parts of congruent triangles are congruent. From here, if that's the case, we now need one last thing in order to say that the two top triangles are congruent, and that would be segment PS. So PS is congruent to PS by the reflexive property. You may be like, well, couldn't I just use PB again? Well, no, PB is the entire segment here. It is further than the segment that we're looking for. So we're looking for this triangle PES. However, PB goes past PS. So we just needed PS here. At this point, we can say that triangles EPS and triangle RPS are congruent. The reason that we can do that is side, angle, side. So these two triangles are congruent by side, angle, side. At this point, again, we're going to go back towards our bisector. So I can say that ES is congruent to SR. And again, we have congruent triangles. So the reason I can say that those segments are congruent is because corresponding parts of congruent triangles are congruent. Now we move towards the angles. We want to prove that's perpendicular as well. So angle PSE is congruent to angle PSR. And again, that goes back to the CPCTC. The triangles are congruent. The angles are corresponding parts within those triangles. So therefore, the corresponding parts of congruent triangles are congruent. Now, if these angles are congruent, which we just showed, and they're supplementary, which makes sense because they form a straight line, then I can say that they are right angles. So angle PSE and angle PSR are right angles, because if two angles are both congruent and supplementary, then they are right angles. Lastly, we can say that PB is the perpendicular bisector of ER, because again, we see that they are bisecting ER. It's being cut in half. ES is congruent to SR from statement 8. And also we see perpendicular. We see right angle intersections. And we see that from statement number 10. So PB is perpendicular to ER, and PB bisects ER. That is enough information to say that PB is the perpendicular bisector of ER. All right, next up, our final proof of the day. Given angle ADC and angle ABC are right angles, and AB is congruent to AD, we want to prove that AC is the perpendicular bisector of DB. So, to get started on this, we already have a side and an angle. Is there anything that's shared by the two bigger triangles? Well, yes, they both have AC. Now, before I do that, I'm going to go ahead and say that angle ADC is congruent to angle ABC. And again, those are the two angles from statement number 1. The reason I can say this is that they are right angles, and we know that all right angles are congruent. From here, again, we see that AC is shared by both triangles. So I can say that AC is congruent to AC, and of course that's going to be by the reflexive property, every single time that something's congruent to itself. From here, we can see if these two triangles are congruent. We have angle, side, side. That's not a congruency postulate for us, though. But we have a right angle. So we could use hypotenuse, leg. And since it's a right angle, that works. So triangle ABC is congruent to triangle ADC by HL, hypotenuse, leg. If that's the case, we are now going to move to smaller triangles. I'm going to use these two really tiny triangles on the left side here. So using these two triangles, again, I need to prove that they are congruent as well. So something that's shared by both the big triangle and the smaller triangles is this angle here, angle DAE. So I can say angle DAE is congruent to angle BAE, because again, if the triangles are congruent, then the corresponding parts of congruent triangles are congruent. I see that both of the smaller triangles share a common segment in segment AE. So I can say that AE is congruent to itself by the reflexive property, which would then allow us to say that the two smaller triangles, triangle DAE and triangle BAE, are congruent to each other. And that would be by side, the green side, the purple angle, and the orange side. So side, angle, side. Well, if those two smaller triangles are congruent, DE is a corresponding part of it, and it corresponds to segment BE. So these are corresponding parts, and they're corresponding parts of congruent triangles. And I know that the triangles are congruent from statement number 8. So if that's the case, I can say that DE is congruent to BE by CPCTC. From here, we focus in on the angles next. So angle AED is congruent to angle AEB, and again, that's by CPCTC. So these two angles right here are congruent as well. From this point, if the angles are both congruent, and I can see that they're supplementary, they form a straight line, I can say that angle DAE and angle BEA are right angles. DEA and angle BEA are right angles. Again, that goes back to them being both congruent and supplementary. So if two angles are both congruent and supplementary, then they are right angles. Lastly, we see that it's being bisected, it's being cut in half, and it's perpendicular. It's intersecting at 90 degrees. So I can finally say that AC is the perpendicular bisector of BD. The reason that we can say that is AC is perpendicular to BD, which we see with the right angles. And AC bisects segment BD. which we can see because it's being cut in half from statement number 9. At this point, this proof is now finished because we have proven that AC is the perpendicular bisector of BD. All right, so we have now finished today's lesson. We've covered 4.5, the equidistant theorems. Again, our learning target was I can write two-column proofs involving triangles, isosceles triangles, circles, and the equidistant theorems. If you guys have any questions or need anything, please let me know. Thank you guys so much for watching today. I really appreciate it, and I hope that you guys have a great rest of your night. Take care.